Assalamu alaikum everyone. So we'll start with a new topic, which is area and volume calculation. So estimation of area and volume is very important in any surveying project because since the estimates that we make are directly used in estimation for the construction, and the correct estimation can result in different economies for the project. So usually earthwork volumes must be estimated. So whenever we have to decide on the route alignment and we need to decide which route a project should take, so that depends a lot on what is the topography of the land. And once we are done with finding out horizontal and vertical control over an area, so we can use those measurements or those estimates to find out areas and volumes. So whatever techniques that we have studied up till now, that data, like we calculated coordinates using a theodolite, so that data can be used to find out area of any project or any scheme, and that combined with levels, we can find out volumes as well. So the use can be very diverse, ranging from uh, construction for a simple house to construction for a dam. So if you want to find out what would be the water carrying capacity of a valley of where you want to construct a dam, so that can be done by using the same surveying principles. So first we'll see the area calculation. So we can have two different sorts of areas: regular areas, so which are like the ones that are enclosed by survey lines. So if you have a closed traverse and it makes a particular shape, so that would be a regular area. And the irregular areas are the ones which you cannot apply a direct equation to them to find out the area, and you need to have a different method to find it out. So for regular areas, we can use a planimeter, which is an instrument that we'll discuss. We have so many mathematical formulas for different shapes. We can use them, and then we have method of coordinates that we are going to discuss. And for the irregular areas, again, we have a couple of methods that we'll see one by one. So for regular areas, you have these different instruments. Planimeters, basically, what they do is that they can directly give you area of uh, or an area which is enclosed by a regular boundary. So you can use these instruments, but we have very advanced instruments now that have taken over. For example, you can calculate areas just simply by taking photographs or by using EDMs. And then by using that data, we can calculate area. So that has more use now. And then we have mathematical formulas for different shapes, so that can directly give us areas. And then we have method of coordinates. So when you have an irregular shaped area, but the sides are joined together by regular lines, then we can use this method of coordinates. So if we have a closed traverse as shown in this figure, where you have 1, 2, 3, 4, 5 as the station points, and these are the lines joining them. And by finding out the coordinates of the station points, we can find out the area enclosed by this traverse. So the method is that you need to draw out a table, and the first column represents the station points. So in our case, we have station point 1, 2, 3, 4, 5, and then the convention is that you write down the first station point back as well, because starting from the first point, you go to the fifth, and then in order to close down the loop, we again join this point 1 with the point 5 using this line. So hence this point 1 over here. And then you write down the coordinates, y coordinates first in the first column, and then the x coordinates in the second column. So for the first point, you have x1, y1. For the second one, x2, y2. And similarly, you reach point 1 again, where you have x1, y1. So if whatever x's you are using, so x1, y1, and x2, y2, so all the coordinates would be written down. And then we have this positive product column and a negative product column. So when you're done with this, completing this table, You join diagonally these points with a solid line and these points with a dashed line. And the positive product, that means x1, y2 would come over here, x2, y3 would come over here. Similarly, you complete this column. And the negative product, which was shown by the dashed lines, so y1, x2 would come over here, and similarly, you will complete this column. And then you'll take the sum of this column and sum of this column, and then use the equation. Area is equal to 0.5 multiplied by the absolute sum 1 minus sum 2. And while you are doing this, since your axis can be anywhere, so we'll retain the sign, whatever signs there are, and then you take the absolute difference and divide it by 2, and that gives you the area. So let's see this question where we have section points A, B, C, D, and E, and we have y coordinates and x coordinates. Uh, and first, we fill out the table. So we would have A, B, C, D, E, and then A, and then we'll copy these coordinates in the next columns, and then we take the positive product like we discussed. So these values 231.66 negative with a 311.26 with the negative, so you get positive 72106. And similarly, if you see this one over here, so that would be negative 311.26 multiplied by 123.48, so you get a negative value over here. Similarly, you complete the table, and at the end you take the sum of the positive products and sum of the negative products, and then you take the absolute difference. So minus, and this minus sign would be retained. So throughout this procedure, the signs would be retained, and at the end you'll take the absolute difference divided by 2, and in the end you get the area. So since we had a negative in the equation and a negative over here in our question, so that means this will become positive and then divided by 2. Now let's talk about the irregular areas, which are more of a concern for us. So for that, we have got a couple of methods. So first, we'll discuss the graphical method. So in this method, what is done is that the area is plotted on a graph paper, and you select the scale for the graph paper. So that would mean um, what are the dimensions of this square box. So in our case, area of each square and the scale is 1 over 1000. So we must have taken uh, a value for the scale. So that means whatever this dimension is, let's say this is 10 millimeters. So 10 millimeters on this paper is equal to something on ground. So if this is 10 millimeters and this is 10 millimeters, that means that the area is 100 millimeter squares. That means the area of one box is 100 millimeter squares, and this would correspond with particular area on the ground. And then what you do is you count the number of boxes within this perimeter. And first you count the number of boxes which are completely inside, and then what you can do is you can commute the area of these partial boxes, and that's a rough procedure. So if I see this box, so I can say that it has been covered by inside the traverse, uh, let's say 20% of it or 25% of it, and this seems to be 40%. So this would be 0.4 plus 0.25 plus whatever we have over here, and that would be partial areas of the boxes covered by the traverse. So first you count the number of boxes completely covered, and then you count the partial areas, add them up, and you can get the total number of squares covered by your traverse, and then you multiply it by the area of one box, and you can get the area on the graph, and then you can convert it into respective area on the ground since we are working with a scale. So this is how the graphical method works. And then we have a mid-ordinate tool. So we've done a lot of times integral, which is area under the curve. So in this case, it's pretty much similar. So this is the irregular area, and we want to calculate the area under this complete curve. So usually you'll be facing this sort of problem a lot of times your next semesters as well. So basically what is done is that the whole area is converted into a number of strips, and each strip boundary is at a particular distance apart. And this D which is the distance between or the distance covered by one strip, is decided by you yourself. And what d value to take depends on how much accuracy do you want. Because in mid ordinate rule, usually what happens is that once you select d, we take the value of this ordinate, which is known, and this ordinate, which is known, and we divide it by 2, and that is taken as the average mid ordinate, and then that is multiplied by the distance, so that you get area of one strip, and similarly the areas of other strips are calculated. So since you are taking an approximation, so the smaller the value of d, that means the number of strips would increase, but the accuracy would increase as well. So this d is selected by yourself. So once that is selected, we take the value of ordinates at the boundaries of the strips, and we take the average of uh, every strip. So once we have the average height or average ordinate of every strip, we multiply it by the distance d. So that means total area is equal to d times this average O1 plus O2 O2 plus d into O2 plus O3 O2 plus d into O3 plus O4 O2. So that means you can take d as common, and the sum of the mid ordinates. So the mid ordinates are the average ordinates at the center. So that means O1 plus O2 O2. So this is how the mid ordinate tool can be used to calculate area. So let's see this example. So we have this curve which has an ordinate of 0 at the starting point and some ordinate value at this point over here. So they have given us the distance as which these ordinates are measured. So we have a difference between the distance of 8. So that means d is equal to 8. So you can draw an imaginary axis at this point and start calculating the distance towards the right. So it's 0 over here and 8 at O2 and 16 at O3. But we are only interested in the value d. So if these distances change, uh, then the d can be different. So it can be 8 meters over here, 6 meters over here, 4 meters over here, and then 8 meters over here. So they can have different d's, but usually they remain the same. So if they remain the same, then obviously you can use it as a common value. Otherwise, you can do it by strip as well. So at each ordinate or at each distance, they have given us the value of the ordinate or the offset. So it's 0 at O1 and O2 is equal to 1.5 and O3 is equal to 2.2 and O6 over here is equal to 1.1. So like the equation that we discussed, that the area is given by d, so d is 8, multiplied by sum of the mid ordinates. So what we have to do is take the average of O1 and O2 and similarly O2 and O3. So that means for the first strip, the average would become O1, which is 0, plus O2, which is 1.5 divided by 2. So here we have the first average for the first strip. Similarly, for let's do the last one, O5 and O6. So we have 2.1 plus 1.1 divided by 2. So here we have the sum of mid ordinates multiplied by d, and we get the total area. Then the next rule is trapezoidal rule, and this rule assumes that the short lengths of boundary between the ordinates are straight lines, so that the area is divided into a series of trapezoids. So previously in the mid-ordinate rule, we assumed that the strips were transformed into rectangles by taking one average ordinate and the base. But in trapezoidal rule, what we assume is that the two ends of the ordinates are joined by a straight line. So this is more realistic uh, since this is not horizontal. Now we are assuming an inclined line so that our strips make a trapezoid. So for this, total area is given by d multiplied by f plus l, where d is the equal distance between ordinates, so like we discussed before, and f is the first ordinate and l is the last ordinate, plus 2 into other ordinates. So that means if we are working with this diagram over here, so according to this equation, we would have uh, d multiplied by 1 plus 7 and plus times the or they have taken this common over here, divide by 2 plus the other ordinates O2, O3, O4, O5 and O6. But what they have done is that they have taken 2 as common. So that means this becomes d by 2 and this becomes 2 into other ordinate. So your final equation becomes d by 2 multiplied by the first ordinate, which is O1, plus the last ordinate, which can be On, whatever the number of ordinates that we have, plus 2 times the all the other ordinates starting from O3, and the last one would become On minus 1 because we have used O1 and On separately, and the other ordinates are multiplied by 2. So we're not going into the derivation of this equation, but if you want to see that, you can Google it and you can see it. But over here, we're just interested in application of these equations. So let's see one question for the trapezoidal rule. So like before, they have given us distances at which the offsets are measured. So again, d becomes 8, and using the equation, the total area is equal to d by 2. So this becomes 8 by 2 multiplied by the first ordinate plus the last ordinate. So O1 is 0 and the last ordinate is 1.1 plus 2 times the sum of the other ordinates. So in this case, you don't have to take the averages. We are taking the ordinates as they are. So O2 plus O3 plus O4 and plus O5, and this gives us this answer. So there is no limitations for this rule. The rule can be applied for any number of ordinates. They mention it over here because the next method that we are studying is for a specific number of ordinates. So it has a limitation, and we'll see what that limitation is. So the next method is Simpson rule, and the Simpson rule states that to the sum of the first and last ordinate, uh, 4 times the sum of even ordinates and twice the sum of remaining odd ordinates are added. This total sum is multiplied by the common distance, which is d, and 1/3 of this product is the required area. So the equation becomes total area is d by 3, where d is again the distance or the distance for every strip, times multiply by f, which is the first ordinate, plus l, which is the last ordinate, plus 4 times the sum of even ordinates, plus 2 times the sum of odd ordinates. So if we see this example over here, we have the ordinate starting from O1, which is this one, and going to O7, which is this one. So if you apply this equation, the equation would become d by 3 into O1 plus O7 plus 4 into even ordinates. So the even ordinates are O2, O4 and O6, plus 2 times the odd ordinates are O3 and O5. So this is the final equation. Now this method has one limitation, and the limitation is that in order to apply this method, the total number of ordinates have to be odd, or the total number of strips have to be even. So in this case, we have 1, 2, 3, 4, 5, 6, 6 number of strips. So that should be even, and that means the total number of ordinates should be odd. That is because this equation is derived considering two strips and 3 ordinates. And when you apply that equation to the complete number of strips, so we get this equation. So this is one limitation for the Simpson rule, and you can see the limitation over here that this rule is applicable only when the number of divisions is even. That means the number of ordinates is odd, and this is the equation over here. So let's try to apply that to our question. And in our question, we have the ordinates starting from O1. So O1 is 0, O2 is 1.5, O3 is 2.2, O4 is 2, O5 is 2.1, O6 is 1.1, and there should be this O7 over here, which is 0 in our case, and it should be shown in the diagram as well, because otherwise this rule is not applicable. So when you apply the equation, the area is equal to d by 3, so d is 8 in this case as well. So 8 over 3 multiplied by the first ordinate plus the last ordinate, so 0 plus 0, plus 4 times the sum of even ordinates, so O2, which is 1.5, plus O4, which is 2, plus O6, which is 1.1, plus 2 times the sum of odd ordinates, so we have O3, which is 2.2, plus O5, which is 2.1, and then you can calculate the area. So what is the difference between trapezoidal rule and Simpson's rule? So in trapezoidal rule, the boundary between the ordinates is considered to be straight, and that makes each strip a trapezoid. Whereas in Simpson's rule, the boundary between the ordinates is considered to be an arc of a parabola. Hence, the derivation has those constants. And since this considers the ordinates to be an arc of a parabola, which is more realistic, more close to the actual shape of the curve, so that means the Simpson's rule becomes the most accurate one. And behind that is the trapezoidal rule, and even behind that is the mid-ordinate rule, because the first rule considers the strips to be rectangle, which is way off from reality. Trapezoidal rule considers the strips to be trapezoids, which is closer to reality, and Simpson's rule is most closest to the reality. That's why this rule gives you the most accurate results. And in trapezoidal rule, there is no limitation. It can be applied for any number of ordinates. But in Simpson's rule, the number of ordinates must be odd. And if they are even, the total minus one ordinates are solved by Simpson's rule, and the last ordinate is solved by trapezoidal rule. So if that is the case, that the number of ordinates is even, and if you still want to apply the Simpson's rule, what we can do is we can take n minus 1 ordinates, and if we see this, we can solve it up till, uh, let's say we have up till O6, or let's see this diagram. Yeah, this fits perfectly. So if we have this question in which we have even number of coordinates, so we can solve up till this point, so this much area with Simpson's rule, and then for this last strip area, we can use either trapezoidal rule or we can use the mid-ordinate rule, whatever, and add the area of this remaining strip to the area calculated for the rest of the curve. So it gives an approximate result for trapezoidal rule, and Simpson's rule is more accurate. Sometimes one or both the end of the ordinates may be zero. However, they must be taken into account while applying these rules. So even if the first and last ordinates are zero, that doesn't mean that you can ignore them, because if we ignore them, that means we would be ignoring this area over here. So we always take their value, whatever the value is. So that was for area calculation. Now we'll take a quick look at volume calculation, which is basically in continuation with the area calculation. Because once you have an area, what's left to be done is to multiply it with the third dimension, the depth, so that we get the volume. So for volume calculation, we can have a number of methods by spot height, which is generally used for small areas such as underground tanks, basements, buildings, and sites. So in spot heights, what we do is we make a grid, and we calculate the areas for each square or rectangle in the grid, and then we calculate depths at the intersections of the grids, and then we calculate the depth depth at the mid of any square or any rectangle, and then we multiply that average depth by the total area, and that is how we do it by spot height. In cross sections, this method is used for long narrow work such as roads, railways, and pipelines. So we'll see how this works. Basically, whenever we dig up earth for these sort of projects, the width that is to be dug remains the same, and the depth keeps on changing. So that is how, by calculating average depths after some distance or some other method, we can use the method of cross sections even to find out the volume in those sort of projects. And then we have contours. So contours are used for large areas such as reservoirs, landscapes, redevelopment sites, and you'll see what contour lines are in the next lecture, or you have seen them, I think, in the previous lecture. Yeah, we have covered contours, so, and we have discussed this in detail, how you can use contours to find out volumes. So first was by taking the mean areas. So the volume is given by whatever areas you have, you add them up, and you take the average, and then you multiply it by the length. So that is basically more realistic when we are trying to find out volumes for projects which are longitudinal in nature. And then we have end areas, for which the equation is d by 2 multiplied by a1 plus an, which is the first area, and the end area, plus 2 times the sum of rest of the area. So this is the equation that we did before as well. But in this case, instead of the linear dimensions over here, we have the areas, and then we multiply it by the third dimension to get the total volume. And then we have the Prismoidal formula, which is similar to the Simpson's rule. So we have d by 3 multiplied by the first area plus the last area plus 4 times the sum of even areas plus 2 times the sum of odd areas, again something that we have seen before. So this is the method of cross sections in which you divide your uh, areas or the total length into a number of cross sections, and then you find out the area for each cross section, and then you multiply it with the third dimension, which is the constant. So earlier the distance between the strips was constant. Now in this case the width of the cross section is usually constant, and you do a number of methods to find out the average areas. So let's see this example. Distance is given to us in meters, and the areas are given to us, and what we need to do is we need to find out uh, the volume using the three equations that we just saw before. So first let's see how to solve it by using the mean areas method. So in that method we have the equation, which is the sum of areas divided by n, which is the total number of areas that we are taking, and then we multiply it by the total length. So this is different from the other equations, in which instead of this total length we take this d value, which is the distance between each strip. So in this case d becomes 0, 15, 30, so that means that difference of 15, so d becomes 15. Whereas in this equation we don't use d, we use the length. So the total length is 90, so we have 90 over here. And in the end areas method, so for this equation we have d by 2, so d is 15. First area a1, which is 11, plus the last one, which is 220, plus 2 times the sum of remaining areas. And in the model method we have d by 3, which is 15 by 3. First area plus last area plus 4 times the sum of even areas, so a2 plus a4 plus a6 plus 2 times the sum of odd area, 64 plus 160, and we get this answer. So the reason why we have this equation for the mean areas method and D instead of L for the other methods is that in the mean areas method, imagine you have a long cross section, and the total distance that we have to cover, for which we have to find out volume, is L. And in this method we calculate areas at different lengths at different stages, and then we take one mean area. And when you take one mean area, you have to multiply it by the complete dimension. So in this, that's why we have L over here. But in the other equations, we calculate volumes for each strip. So in that case, instead of L, we are using D. So that is it for this topic for calculating areas and volumes, and I'll see you in the live lecture.